All right, folks. So I wanted to do one more example, calculating eigenvalues, calculating eigenvectors. And so I took this example from the book. There's a matrix A, it's 3 by 3. Let's start by finding the eigenvalues. Of course, I can't find eigenvectors before I know any eigenvalues. So to do that, we need to set up our characteristic polynomial, characteristic equation. So let me start by doing that. So I need to calculate this matrix A minus lambda I. In this case, 5 minus lambda. I'm going to subtract lambda from the diagonal. Minus 2, 3, 0, 1 minus lambda, 0, 6, 7, minus 2 minus lambda. Okay. And the characteristic polynomial, as you remember, is just the determinant of this matrix. Now, to calculate this determinant, we of course should be using some cofactor expansion. I notice here that because I have a row 2, which has a bunch of zeros in it, it makes a lot of sense to do a cofactor expansion across the second row. And so to do that, I notice that this is okay, plus 1 minus lambda times the remaining 2 by 2 matrix I get by deleting the second row and column. And so I'm going to have a 2 by 2 matrix, 5 minus lambda, 3, 7, 6 minus 2 minus lambda. Okay. And then everything else is 0, so my cofactor expansion is just this one term. And I can continue by calculating the determinant of that 2 by 2 submatrix. So let's go ahead and do that. 1 minus lambda times. So I can cross multiply to get my 5 minus lambda times minus 2 minus lambda minus 6 times 3, which is 18. Okay. So we know we're going to want to factor eventually. So let's continue by evaluating, distributing, simplifying, right, and refactoring. Of course, I want to leave that 1 minus lambda in front because it's already factored out for me. So, I'll leave it out as a factor term and really focus on the things inside the brackets. So I'm going to have a 1 minus lambda times. So if I distribute lambda squared, minus 5 plus 2 is minus 3 lambdas, and then minus 10 and minus 18 still left over. Okay. So continuing to simplify, what are we doing in space? Yeah, so some space down here. 1 minus lambda times the quadratic lambda squared minus 3 lambda minus 28. Okay. So can I factor that quadratic? So it looks like I might have some hope here. So 28 has factors 7 and 4, and then 7 and 4 can be combined to create a -3. So yeah, this looks promising. So I'm going to factor this as lambda minus 7, lambda plus 4. The -7 times +4 is the -28 constant. And the inner and outer terms combine -7 plus 4 minus 3 lambda. Okay, good. So this is my characteristic polynomial. It's nicely factored into 3 pieces already for me. But to find my eigenvalues, of course, I need to set this equation equal to 0 and solve for the lambdas, which we can see from the linear factors. So setting up my characteristic equation would tell me I have 3 eigenvalues, 1, 7, and minus 4. So in this case, I do get 3 eigenvalues. Okay. An interesting question that came up after class was, well, what happens if I have not real roots? So of course, you could study those. That's very interesting. But for our class, we're really only going to want to think about those real roots for now. Okay, so in this case, I did get all 3 real eigenvalues. Don't get any complex numbers, which is nice. Okay, so those are my eigenvalues. At this point, we could continue by looking for associated eigenvectors for any number of those eigenvalues. So because it's very repetitive, let's just do one of them. For example, let's do lambda equals 7. Okay, let's find an eigenvector. And in fact, let's find all the eigenvectors associated to the eigenvalue 7. Okay, so I'm going to copy my answer here so I don't lose it. 1, 7 minus 4. And then I'm going to reset my board to calculate eigenvectors. Okay, so remember for eigenvectors, specifically for lambda equals 7, I'm going to focus on. I now need to solve the associated equation a minus 7i times x equals 0. Okay, I'm looking for the null space of that matrix, a minus 7i. So setting up this as an augmented matrix that I can row reduce, I'm going to have what? I'm going to have 5 minus 7 is minus 2, minus 2, 3. Okay, I can add the zeros if I want to remind myself. 0, 1 minus 7 is minus 6, 0, 0. And then 6, 7, minus 2, minus 7 is minus 9. Okay. And I now need to start row reducing to find my solution set, right? So I'll start by, I'm going to leave the first row as is because it won't divide super nicely. I noticed I could actually multiply row 2 by a negative 1/6 or divide by negative 6 and make it to 1. Okay, why not? But really my focus is using this negative 2 in the top left pivot position to cancel out the 6 below it. So I see I need to multiply row 1 by 3 and then add it to row 3. So negative 2 times 3 is negative 6, plus 6 is 0. Negative 2 times 3 is negative 6, plus 7 is 1. And 3 times negative 3 is negative 9, plus sorry, I multiply by positive 3, right? Multiply by positive 3. 3 times positive 3 is 9, minus 9 is 0. Okay. And that's good. You know, I can sort of check myself here. I know that I should have a free variable. And after this calculation, I do see that by using row 2, I can cancel out the 1 in row 3. I'm going to have a free variable as a result. So if I did this wrong, I would have, you know, sort of a full rank matrix, which is bad, right? I want to make sure I have a free variable here. All right, so continuing, minus 2, 3, 0. As I said, you can use that 1 to cancel out the 1 below it. And in fact, I could also multiply by 2 in row 2, add that to the row above to get a 0 even here. So now it's even nicer. I have this in a nice echelon form. Why not? I'll even divide by negative 2 to make it, and the first row to make it row reduced echelon form. So this will be a positive 1. This will be a minus 3/2. Okay, so now I'm in row reduced echelon form. So it's much easier for me to look at this and write down my solution set. So I see that I'm going to have x1 equals 3/2 x3. I have x2 equals 0, and x3 is free. Okay. Well, let me delete some of my matrices. At this point, I have my solutions written out in sort of equation form. I want to write them in parametric vector form to write down a basis, say, for my eigenspace. So I'll delete my previous work and really focus on my parametric vector form, x equals x1, x2, x3, which in this case is, okay, so x1 is 3/2, x3, x2 was 0, x3 is free, which gives me 3/2, 0, 1 times the free variable x3. So if I want an example of one eigenvector, so the eigenvector 3 halves 0, 1 is one eigenvector for the eigenvalue 7, right? Because we started this with lambda equals 7. In fact, this forms a basis for the eigenspace, the 7 eigenspace. So if I wanted not just the single vector, but I wanted, say, a basis for the 7 eigenspace, in fact, there's only one free variable, there's only one generating basis vector, that 3 halves 0, 1. So that is one example of a vector, an eigenvector, but in fact, it also is a basis for the entire eigenspace. We see in this case, the eigenspace is one-dimensional. Okay, so that covers a lot of stuff, right? So we saw how to use we saw how to use the characteristic equation to find the eigenvalues, 1, 7, minus 4. Once we have those, we can solve the associated equation a minus lambda I times x equals 0 to find eigenvectors or even basis vectors for the eigenspaces. Okay, so that's all of chapter 5 sort of, 5.1, 5.2, all sort of summarized. If you have any questions, please let me know. I hope this example was helpful.